Hi, I'm Paul Smolensky, and I'm going to talk about something a bit different, probably, than what you've been hearing in classes. I'm going to talk about the relation between generative linguistics and the cognitive science of language in the large. Can you hear me in the back okay? Let me know if there are any problems. My voice may start to go. So in generative linguistics, there are a bunch of questions which are often asked and seriously worked on. How are linguistic representations structured? How are grammars structured? What is universal among languages? How may possible human grammars differ? Are grammars learnable in principle? So these are the kinds of questions that generative grammarians have made a lot of progress on. But then there's another set of questions which have gone relatively unattended. Are symbols the right way to characterize language in the mind? So generative grammars take for granted a computational system of symbol manipulation. Is that actually the right way to deal with human cognition in the domain of language? If so, where do the symbols come from? How are they realized in the brain? What allows us access to these strange things that we build our grammars out of, given that they have to somehow reside in our heads? Exactly what are the processes that build linguistic representations, and how do they embody and use that grammatical knowledge to do it? Exactly which algorithms does the mind-brain use to learn grammar? And I just use this because some of the algorithms are trafficking in mental stuff and others in more neural stuff. How can quantitative variation and errors be explained? So when psychologists study language in the laboratory, they're busy collecting data about errors that their subjects make under various conditions and what we can learn from those errors, what kind of variation you observe in behavioral responses to linguistic stimuli. How can those things be explained, given what we know from generative grammar? How can the temporal properties that are observed also in the laboratory be explained? So I will talk about all these questions today and try to argue that generative grammar does have something important to contribute to dealing with these questions, as well as the ones that are more classically the internal questions of linguistic theory. I'm not sure why we're getting cut off here, but if anything seriously gets omitted, we'll make do. Okay. Okay, so starting with the first question, are symbols the right way to characterize language in the mind? Well, for this question, I want to set a little bit of historical context. And in this discussion, as in pretty much all of them, I'm going to be dealing at a very, very simple, superficial level. And so those of you who are already familiar with some of these areas will immediately see the simplifications that I'm making. But it's late in the course, it's late in the day. Hopefully, it won't strain your brain too much to operate at this level. So a little historical context for this question. So the type of elements and operations that are employed by the mind form the cognitive architecture. That's what a cognitive architecture is. It's a specific type of computational architecture. The reason we think that the cognitive architecture is a computational architecture is because we have pledged ourselves in cognitive science to this proposition. Now, the question then of cognitive architecture is, what kind of computational system do we have in the mind as regard different cognitive domains, language, the one of interest to us? So at the beginning of cognitive science in the 50s, the cognitive architecture that was presumed by everybody was the symbolic cognitive architecture, virtually everybody. So not only was Chomsky deploying this in establishing modern generative grammar, but John McCarthy, not the phonologist, the computer scientist, was using it to set up the field of artificial intelligence as a kind of logic. Newell and Simon were setting up computational systems for modeling human problem solving as a kind of system of symbolic pattern matching procedures and symbol manipulating operations. So there was a very vigorous yes to this question that reigned in the field for decades. But then in the 1980s, this approach to the cognitive architecture called parallel distributed processing, or PDP, or connectionism, or neural networks, variously, became a prominent candidate for what the right way to characterize human cognitive architecture might be. And the proponents of this took the position that symbols were just the wrong kind of computational medium for characterizing human knowledge. Now, so the names that are associated with the establishment of this view, Rommel Hart, McClelland, Jeff Hinton, Stephen Grossberg, they are the analogs of the Newell and Simon and Chomsky and McCarthy for this cognitive architecture. And rather than having symbols as the basic elements of the architecture, what you have are these things called units, which have different degrees of activation, and they form large networks that are interconnected with strengths, with connections that have varying strengths. So the elements of the architecture are these activation values of units, which are sometimes called neurons. They're certainly inspired by neurons, and the computational architecture that is being explored in this work is intended to be more faithful to the style of computation performed in the brain than standard symbolic computation is. So the kind of operations that manipulate these elements in this architecture are operations of spreading activation. So the activation of a unit influences the activation of the units it's connected to, exciting them, raising their activation, or inhibiting them, depending on whether the connections are positively weighted or negatively weighted. And there is a change in these strengths of connection. The weights on these connections change with experience via learning rules that are a kind of modern-day implementation of empiricism. And what the proponents claim to be exploring it is what they call the microstructure of cognition. They're trying to work at what they perceive to be a more fine-grained level than the level at which symbolic computation has been carried out. What symbols correspond to are large-scale activation patterns. So a symbol in a tree, which might represent a structural description for, say, a syllable, a tree composed of multiple symbols, would be for the PDP people some kind of activation pattern spread out over a whole lot of these units, where the particular activation values, the pattern that they form, is what encodes that particular tree. And the patterns that are the contributions of the individual constituents of the tree all overlap with one another and add up, and they're not separated into different places in the network. And for these people, symbols are kind of an approximation for describing the large-scale patterns in the network. And variously, they're seen as quite crude approximations or maybe not so crude approximations, depending on the work. Now, in the 90s, I developed an architecture which I call the Integrated Connectionist Symbolic Architecture, the ICS architecture, which I'm going to tell you about, in which I tried to take a position other than what most of the advocates of these two were taking, namely, rather than trying to argue that one of these was the right way to go and the other one should be abandoned or ignored, I tried to say that it's important to recognize that the symbolic cognitive architecture is not just a crude approximation, but has some extremely important, accurate things to tell us about cognition at the level of these activation patterns. At the what I'll call the macro level, the aggregate patterns in the network, which correspond to symbols, we know a lot about their character because of what we've learned in generative grammar and other symbolic cognitive theory. But at the same time, there's another level that needs to be taken seriously, the micro level, where the processes live that actually build these representations. So the trees that we talk about as structural descriptions in phonology or in syntax are built by spreading activation. The job of the network that encodes our knowledge of grammar is to build the right patterns by spreading activation. And so what we've learned from PDP work about how those kind of computations can be done and can be learned is extremely relevant to the picture too. So the idea is that we need to look both at the macro level and the micro level, and when we do, we see on the one hand a symbolic architecture and on the other a connectionist or neural network architecture. So trying to make that formally precise is what this research is about, and what I'll tell you about today is some of the results of doing that. You can find out more about it in the book that lays it all out, The Harmonic Mind, and 2 volumes. Everything I'm going to talk about, with one exception, which I hope to remember to tell you about, you can read about in here. Okay, so back to that list of questions unasked. Are symbols the right way to characterize language in the mind? Well, I'm going to pursue the hypothesis that they are, as long as we understand that they are one level of description, and that the processes that build them and manipulate them and the knowledge about how to do that may need to be thought about at a more microscopic level if we're going to understand how the system actually embodies and uses its knowledge. So where do the symbols come from? How are they realized in the brain according to this picture that I've given you so far? As I said before, symbol structures are activation patterns. And rather than think of this as kind of a metaphor, we're going to take this extremely literally. So the mathematics of this architecture makes very precise what it means to say that this symbol structure is realized in this activation pattern. It does that by formalizing activation patterns as vectors. So if you take all of the units in a network and list all their activation values at a given time, and they go up and down as you go across the network, that's the pattern. That list of numbers, the activation values, is a vector. And the fundamental proposition of the PDP architecture is that mental representations are vectors. And computation on them is the kind of computation you expect on vectors, not on symbols. Okay? The reason that one doesn't completely eliminate the other from the picture is that it turns out there's an important isomorphism between, on the one hand, symbolic operations, the things that, for example, relate a tree to its internal constituents, the relationship of constituency. That's kind of symbolic operation or relation, has a counterpart in relations among vectors. And by isomorphism, what I mean is that we can spell out in detail how particular symbolic operations can be realized in particular operations on vectors. So the activation for vector for a tree, for example, is a sum of the activation vectors for its constituents. So we add together, we superimpose distributed activation patterns for the onset of the syllable, for the nucleus of the syllable, for the coda. They all lie on top of each other, add up to form a pattern of activation which represents that constituent, that syllable, the tree. And the activation vector for each constituent has internal structure, which is crucial. It's the product of activations of two types, of activation vectors of two types. One are vectors that encode the content of the syllables, that individuate the different phonemes from each other, for example. And the other are vectors that individuate the different positions in the structure, the positions in the tree. So there's a vector which specifically refers to the onset position in a syllable. There's a vector that specifically refers to the phoneme k, and it's their product that constitutes an onset consisting of a k consonant. And that superimposes with the corresponding patterns of activation for the other elements in the structure to build up the pattern for the whole syllable or the whole word. The isomorphism that I mentioned allows us to take a class of recursive functions over trees and realize them in connection patterns that compute these recursive functions in one step, not by stepping through the kind of extraction, manipulation, and construction that traditional symbolic computation uses to define and carry out these functions, but rather in a kind of massively parallel way that is realized just by spreading activation. So here's a picture of that. Okay, so here's our input. At the macro level, it's a kind of tree. Here's our output at the same level. It's a different tree. So I'm imagining a recursive function which is going to perform an operation like extracting the subject from this, moving it down here, and extracting some kind of embedded complement and putting it here, taking the verb, putting it here, something which takes a passive sentence structure, reconstructs a logical form for it. It doesn't really matter. There's a class of tree manipulations, which this is an instance of, that can be extremely complicated. And the isomorphism allows us to realize those in the following kinds of networks. So the first tree, as I said, is the input. The second one is the output. We're interested in the function from one to the other. And the way we're going to realize that is not at the level of operations on symbol structures, but at the micro level. So we have to push down to the micro level this input. So it's a pattern of activation. There it is. Each circle is a unit. White means positive activation, black means negative, and the area tells you the size of the activation. So that's a pattern of activation, which is exactly the encoding of that tree, using the kind of methods I just described very hand-wavily, but which can be described precisely. There's a corresponding pattern of activation, which encodes the output tree, and the function's job is to take this pattern and produce this one. Of course, to take all the patterns corresponding to all the relevant trees and produce the correspondingly correct patterns for all the correspondingly correct output trees. And that's done by as follows. That operation from input to output is done by spreading activation. So we have a set of connections that come out of the input units that send activation out. Another set of connections that take that activation and direct it towards the output units, so activation's flowing from the input to the output units. And at every juncture, there's a weight. So this is the weight matrix. At each juncture, there's a number that tells us how strong is the connection from one input unit to the corresponding output unit for that particular junction. And again, white is positive, black is negative, size is indicative of magnitude. And this is the particular weight matrix which implements this particular recursive function. And you can demonstrate that it will always produce the right result. Okay, so the general picture here, which we're going to pursue to more interesting cases, is that we take seriously the idea that symbolic representations are psychologically real. But we think about the processes that construct them as processes like this, not as parsing algorithms or Lisp functions. Okay, so where do the symbols come from? How are they realized in the brain? As these kind of overlapping patterns of activation with the internal structure that I tried to give you a feeling for. Exactly what processes build these linguistic representations? How do these embody knowledge? Well, I gave you an example of a kind of network that does something which is a relevant kind of symbolic manipulation, but it's not something that's particularly interesting from a grammatical perspective. So we'll talk about grammatical knowledge now. So this kind of network I just showed you is a one-shot feed-forward network. The activation leaves those input units, goes through all those connections, feeds into the output units, they get their values, it's done. So it's a one-shot network. Activation goes in one direction, it's feed-forward. Another type of network is more interesting. It evolves over time, so it takes a while before the output pattern is established. It doesn't just happen like that. And that's because there are feedback connections. Activation circulates around. And it takes a while before the output pattern stabilizes into some pattern which it maintains, and that's the output. An important mathematical result that was developed in the 80s by many people working in this area is that many of the networks of this type, these feedback networks, can be understood as performing a certain kind of computation, and that is optimization. They can be seen as maximizing something I call the harmony. This thing goes by many different names. It's been called the energy, it's been called the goodness, it's been called the Lyapunov function. I call it the harmony. So what it measures is a property of the state of the network, and as activation circulates through this feedback, through the feedback loops, what's happening is the network is building the pattern of activation, the representation, that has the highest harmony, that is optimal if we think of this harmony as measuring something like well-formedness. The way this harmony is computed depends on the details of the network, but the core of it, which is common to all networks, is this. The harmony is gotten by looking at all the connections in the network. For a given connection that goes from unit alpha to unit beta, you take the strength of the connection, the weight, between those two units, W alpha beta, you multiply it by the activation of the incoming unit, alpha, and multiply it by the activation of the outgoing unit, beta. That number is the contribution to the harmony from the connection between alpha and beta. And you merely sum the contributions over all the connections in the network, and that's the harmony, or that's the key part of the harmony, the part that depends on the weights, which is where the knowledge is. So these networks are doing a kind of optimization, and what I want to show you now is that we can think about that optimization in terms of constraint satisfaction. We can say that what it means to find the representation with maximal harmony is to find the representation that best satisfies a set of constraints. So to do that, we're going to look at a very simple kind of network first. It's a purely localist network. So this is the kind of network that has been used widely in modeling psycholinguistic experiments, where you have a bunch of units that designate different constituents that might be present in a structure that the speaker or hearer is building or processing. So this is a unit whose interpretation is the consonant K in the onset of a syllable. This is the phoneme E in the nucleus of a syllable. This is the connection between them. Now, there will be lots of other units for lots of other constituents in the network, but we're just focusing on this one connection. The harmony that it contributes, you'll remember, is the strength of the connection, negative 0.6, times the activation value of this unit times the activation value of that unit. So how can we think about that? Well, I claim we can think about that as the constraint star key. Okay? So languages that palatalize before high front vowels might say key is bad, it should be chi. Okay, this is a reasonable constraint. And I claim that this simple connection is a realization of that constraint. Why is that? Well, suppose first that this unit is active. Suppose its activation value is 1. That means we're representing a syllable in which the nucleus is the vowel E. Okay, well then, what are the possibilities? Well, this could be active or it could be inactive. If it's active, then we're talking about the syllable which has onset nucleus key. What do we get? Well, if it's active, then we get a harmony value of 1 times negative 0.6 times 1, or negative 0.6. We get that harmony value. If instead of putting k in the onset, we put something else, ch or whatever, this activation will be 0. What's the harmony? 0 times that, or 0. The point is that 0 is better than negative 0.6. So if we're talking about a syllable with this nucleus, the representation is better if it doesn't put that consonant there than if it does. What that means is what this is enforcing is a constraint against that combination of segments. Yes? Well, if we were trying to, for example, compute the surface form for a word whose underlying form had these two segments in it, then what we might have is some activation coming from the underlying form, the pattern of activation for the underlying form, which tries to activate these two units. But then there are connections among all the units for this representation of the surface form, of which this is one. And the activation will circulate around trying to find the best activation pattern. And if we've set up the connections right, this being one of them, the output pattern will not actually represent ki, it'll represent chi. Okay? Another unit will end up being active because the harmony that results is higher. Okay, so if the nucleus is this vowel, then we actually lose harmony by choosing this consonant for the onset. If the nucleus is some other vowel, then this unit has activation 0, and the harmony contributed by this connection is 0 times this times whatever. It's 0 no matter what. So if the nucleus is not this vowel, then this connection exerts no influence on the choice of k, which is the other aspect of this constraint, which is that when the vowel is not E, it should not be trying to turn off k in the onset, and it doesn't. Okay, so this is a kind of network that I called purely localist. It's not the kind I was talking about before, in which the onset constituent is a distributed pattern of activation, and the nucleus constituent is another distributed pattern, and they superimpose on each other to encode the syllable. Rather, it has activation patterns which are localized to activation to a single unit. That's what it means to be localist. But it turns out that the same constraint can be embedded in a matrix of interconnections W. The way you can think about it, maybe, if you're used to thinking like this, is that in the network in which we have activation patterns that are distributed, so K in the onset is this pattern, and E in the nucleus is this pattern, and they superimpose. In that space of vectors, we can change our coordinates and describe them in a different way. We can rotate our coordinate system in such a way as to take the distributed pattern for K in the onset and make it into a single non-zero value for a coordinate in the direction that points along that pattern. So if we change our description of the vectors to this new coordinate system, we can take a system which is really distributed and give it a description as if it were local. And what we can do is then say, well, in this new description, this constraint is just simply this connection. And then we can go back and say, okay, well, what would that connection look like in the original basis in which the patterns are really distributed? And it spreads out all over the place. It becomes connections all over the network. but connections with the special property that if we describe the whole set of them in this other coordinate system, it would just be this one here. Anyway, the point is that the mathematics of vector spaces allows us to do tricks like this, to encode in distributed patterns the kind of constraints that we need to express harmony relationships like this between distributed vectors that encode constituents. Okay. All right, so the first mathematical result that I was telling you about then is that there's a class of networks, recurrent networks, which can be understood as constructing representations that best satisfy constraints. Here's another result. We can ask if the activation patterns in this network are the kind that we talked about before, which encode symbol structures. Then what? They're not just any old activation patterns. They're activation patterns that realize symbol structures. Well, if the activation pattern realizes a symbol structure, then the harmony of the activation pattern can be expressed in this form. It's the sum of a bunch of terms. Each term is a number which encodes the well-formedness of a particular pair of constituents, symbolic constituents, being in the same structure. So if this were the constituent K in the onset and this were the constituent E in the nucleus, then this well-formedness number might be negative because we have this constraint against that particular pair occurring in the same structure. Other pairs of constituents might be favored by our constraint set, and they might contribute positive harmony instead of negative. But the harmony of the entire activation pattern can be computed either in terms of the weights and the activations at the micro level or in terms of the constituents at the macro level. So we can think about what's happening when activation spreads in this kind of network is that the network is computing the activation pattern which realizes the symbol structure that is optimal, that has maximum harmony when harmony is defined in this way, as penalizing and rewarding particular combinations of symbolic constituents. That set of penalties and rewards, that set of constraints, is what we call a harmonic grammar. So I'm going to show you that again in a somewhat more pictorial form. And maybe 2 passes through it will make more sense than 1, maybe not. But I'm basically just going to run through the same thing again a little bit more pictorially. So we're asking about what does harmony maximization look like when the activation patterns are realizations of symbol structures. So we can think about the question as this. Here's a symbol structure for the syllable cat. We want to know what is its harmony. By that, what we mean is that syllable is realized in our network as a certain activation pattern. So let's go from the macro level down to the micro level, and we get an activation pattern. Here it is. That's the pattern of activation for this syllable. We want to know what the harmony of that representation is. Well, you know the formula for that. It's the sum of the products of the weights times the activation values that the connections connect. As I said, this mathematical result is that this thing is equal to that. This now, however, is an expression that doesn't refer to activations and weights. It refers to the constituents we started with in the first place, like the k and the a. So we can forget about the micro level if we want to and work at the macro level in terms of this kind of harmonic grammar. What are examples of the terms here? Well, we talked about the example of star key, but here's a couple of other examples. So remember, each of these terms in the harmony is a number that reflects the well-formedness of a pair. So let's take, for example, the pair consisting of the syllable node and the T in coda position. Okay? That has a certain well-formedness value. Well, what we know is that in real grammars, that number is negative, because what we know is the well-formedness of syllables is reduced when they have codas. This is the constraint that we call no coda. And so this number, part of that expression being negative, is an expression of the relative ill-formedness of codas. And that's in contrast with this other term, which involves a different pair, the syllable node and the onset constituent. That we recognize as an encoding of the onset constraint. And so that value will be positive because syllables with onsets are better than those without. So in real grammars, these terms have these signs and encode meaningful notions of relative well-formedness. And this is just the same sort of thing we looked at earlier from a different perspective. Okay, now, the idea then is that the grammar is going to generate the representation that maximizes this harmony function that best satisfies the constraints, which are all these different terms with different strengths associated with them. So this is a negative number, but it might be large, it might be a big negative number, a small negative number that would impact how costly it is to put a coda into a syllable. And the representations that this kind of grammar singles out as the grammatical ones are the ones that best satisfy that set of constraints in the sense of maximizing that. Yes?
So this presupposes that we have a set of candidates, and an input that wants to be represented in a set of candidates. And all this should be defined at the order level by other structures, by other non-structures.
We'll get there, but you can think about there being terms here which constitute constraints of faithfulness, in which the constituents that are being paired are a constituent in the underlying form and a constituent in the surface form. And the constraints that say that they should be in correspondence will be positive terms that reward having, for example, this in the surface form if it's present in the underlying form. And those positive values will be competing with this negative one. Okay. Now, in a second, we'll come back to the idea that what it means to say that the grammar is singling out as the structures that are well formed as the ones with maximum harmony. We can think about that as identifying the representations that minimize markedness. So we'll be making a connection to markedness shortly, and I'll remind you what markedness is in a moment if you have forgotten. Okay. All right. So we don't need to talk about that. Actually, given the time, I have to skip the discussion. So one of the things that you'll find in the book is an application of harmonic grammar to the problem of unaccusativity, in which the constraints that are identified are constraints that encode the universal tendencies for properties of aspectual properties of verbs, properties of their arguments, and the inherent structural preferences of verbs for deep subjects or objects, all encoded as constraints of this sort in a grammar that is designed to tell us what's going on in a set of sentence constructions in French, which are tests for unaccusativity. But I'm afraid I have to skip that. We can maybe come back to it if we have time. Okay, bear with me here. Okay, so the question that we were talking about was, what exactly are the processes that build linguistic representations? How do they embody and use grammatical knowledge? Well, this is a kind of answer to that question. The connections in the underlying network are realizations of constraints among symbolic constituents. And they encode a harmonic grammar And it's the activation spreading processes in the microstructure of this network, which actually are the processes that use that grammatical knowledge in order to construct well-formed linguistic representations. So, as I hinted a moment ago, what we have here is a kind of convergence between the study of computation in these neural network-like devices on the one hand, where the concept of harmony emerges as an analytic tool for understanding what these networks are doing, what kind of outputs they're building, and the notion of markedness in linguistic theory. So the constraints that constitute the harmony function when we look at them at this macro level are constraints like no coda and onset. These are ways of encoding relationships of markedness that were identified in the 40s as important grammatical characterizations of linguistic representations. And so what this convergence does is direct us to markedness as the building blocks of grammar. So we'll be pursuing this for a little while, what it means for markedness to be the building blocks of grammar. So in the Prague School linguistics circle, the notion of markedness, again, everything I'm saying is oversimplified. The notion is that each dimension of variation among linguistic representations, or each opposition, syllables that have onsets, syllables that don't, sentences that have subjects, sentences that don't. On each dimension of linguistic variation, each opposition, there's a marked pole, a dispreferred pole. So we have the unmarked or preferred and the marked or dispreferred, and that this is a fundamental organizing principle of grammar. And for our purposes, an important point is that their observation was that these markedness relations are universal. So this is something that you see consistently across languages, that syllables with onsets are better than those without, for example. So this way of thinking about grammar leads us to a certain way of characterizing what's universal in languages. So it takes us not only to markedness as the building blocks of grammar, but markedness as the building blocks of universal grammar. And that's what we're going to try to run with for a little while now.
Convey more information. It is preferred, but it is used anyway to convey more information, some crucial part of information.
Fine.
How does that enter?
It doesn't. It enters into your theory, but doesn't enter this theory. I mean, that is to say, eventually when we talk about probabilistic versions of this grammar, then we might be in a position to try to connect information and markedness. But it's not something which is in the core of the theory. It appears possibly, I'm not entirely sure, when we embellish the theory in probabilistic directions. I mean, but we can certainly say this, that the only reason languages ever use marked structures is because they couldn't convey any information if they didn't. So that we can safely say. Okay. All right, so we've talked about this, and I'm going to shift now back to what the view of processing and representations that we've been led to so far has to contribute to the questions that generative linguists do ask. So what we're going to now talk about is how this perspective, what it tells us about how grammars are structured, and what it tells us especially about what's universal in languages. So the story continues as follows. the first kind of contribution of the integrated connectionist symbolic architecture, ICS, to grammatical theory is a notion of constraint interaction that harmonic grammar encodes. We've talked about that. That's where we encode the strengths of constraints numerically, and we sum together the contributions of all the constraints when we evaluate a given representation. But there's another kind of constraint interaction which is important to discuss, and this takes us to another level in the theory. So at least one useful way of looking at it is we have the neural network level, the lowest level, where representations are numerical and strengths of constraints are numerical, because they're the strengths of the weights in the network. We have a higher level, which we've talked about so far, the level of harmonic grammar, where now the representations are symbolic, they're not numerical. But the constraints are still numerical, and that's still the mode of interaction among the constraints. When we go up to this highest level of optimality theory, then not only are the representations symbolic, but the interaction or the strengths of constraints becomes non-numerical also. And I'll show you how that goes and give you a little bit of a feeling for why. So in optimality theory, constraint interaction is encoded in strict domination hierarchies, where one constraint strictly dominates another one. So in these hierarchies, every constraint has complete priority over all the lower rank constraint combined. This is not generally true when constraints' strengths are encoded numerically. There's a special kind of strictness to the interaction in optimality theory that goes beyond what harmonic grammar provides, although you can approximate it using numbers if the strengths of the constraints grow very rapidly as you go from the weakest to the strongest ones, so that violating a higher ranked constraint gives you such a high penalty that no matter what the lower ranked constraints might have to say about it, they can't possibly add up to anything that's going to override what the stronger constraints have to say. So you can implement this kind of strict domination numerically if you want to, at least approximately. Now, why is it that optimality theory adopts this view of constraint interaction and goes beyond harmonic grammar in this way? Well, basically, it's because grammars can't count. So here's an example of a situation where the kind of counting that grammars can't do would be predicted by a harmonic grammar theory of constraint interaction, but will not be by the optimality theory of constraint interaction. So here's an example of a problem where we're trying to figure out what syllable to stress in a word that consists of a heavy syllable initially, followed by a bunch of light syllables, n light syllables. And the constraints that are going to be relevant here is a constraint that says stress the heavy syllable, and a constraint that says the main stress should be at the right edge of the word. These are two candidates. This one has the first syllable stressed. This has the last syllable stressed. There are other ones that have intermediate syllables stressed, but they're not possible winners. We're not going to talk about them. This candidate here with the initial stress satisfies stress heavy, and that's why there's nothing here. But it violates main stress right, and it violates it once for every syllable that intervenes between the stress syllable on the right edge of the word. So it violates it n times, and that's why we have n stars there. So in harmonic grammar, this constraint has a strength called W main stress right. And the penalty that this candidate gets from that constraint is n times negative. It's a negative value. So n times negative W is the penalty. Now this one, on the other hand, satisfies main stress right, that's why there's nothing here, but it violates stress heavy because the heavy syllable here is not stressed. It violates it once, so we get one violation of stress heavy, one penalty for of this strength and n penalties of that strength. Which of these is optimal? Which has the higher harmony? That is to say, which has the least penalty? Well, it's not very, it's not rocket science. the stress is on the initial heavy syllable if and only if the number of light syllables n is less than the ratio of the constraint that wants to put stress here to the constraint that wants to put stress there. Now, if we're trying to use our theory to do something harmonic grammar wasn't originally actually designed for, which is typology, which is to try to characterize what are the possible languages and not describe languages which are not possible languages, then if we try to do that, and our theory is that these weights in harmonic grammar could be anything, even if we constrain their signs, in respecting the Markedness schools, the Prague schools dictum that we can't change from one language to another, which constitutes the marked pole and which constitutes the unmarked pole, even if we constrain the signs, but if we let the magnitudes vary, then this ratio could be any number. So if that were our theory of typology, we would predict that for every number, there is a language which will stress the first syllable when it's heavy, and then shift to stressing the last syllable as soon as the number of light syllables passes that magic threshold n. Okay? So those are languages precisely which have to count. And those are exactly the kind of languages which we believe don't exist. Okay, so this is not a good theory of typology. Now, what does optimality theory do? It says that instead of thinking about the penalties as numerical, or if you prefer, putting very strict constraints on what the numbers are that are allowed, either this constraint strictly dominates this one, or the other way around. Those are the only two possibilities. If this one strictly dominates, then this one wins, no matter how many syllables n has. No matter how many times this is violated, the higher rank constraint takes priority. So if this is the higher rank constraint, this will win, no matter what n. If this is the higher rank constraint, this will win, no matter what n, and grammars don't have to count. Okay? So that's an example of the kind of thing that led us to postulate that constraint interaction should be by strict domination and not by numerical trading off. Now, in recent, last year or two, Joe Pater especially, and colleagues, including Paul Boersma and others, have been arguing that we gave up on harmonic grammar too fast. That, in fact, pathologies like this can be avoided, and that doing typology with harmonic grammar is something we should take seriously. I won't go there, but I just wanted you to be aware that that's in the works. Okay, so in optimality theory, constraints are ranked in a strict domination hierarchy. That's how they interact, with the higher ranked constraints having strict priority over all the lower ranked ones. And further properties are key. Constraints are universal. So there's this universal set of constraints called con. The set of possible outputs, the candidates, form a universal set produced by this function called gen. The theory takes the strong position that human grammars differ only in how the constraints are ranked. So that if you want to find out what constitutes the set of all and only the possible languages with respect to some module of the grammar, say stress theory, then what you need to do is to look at the n factorial ways of strictly ranking your n constraints. And each one of those is a possible language and nothing else is. Of course, many, many of those will give rise to the same language. So the number of distinct languages that come from that will be vastly smaller than n factorial. But it's a closed form expression for what the set of possible languages is. And I believe it's the first true contender for a formal theory of cross-linguistic typology. What it means is that in optimality theory, there's no such thing as doing language-particular linguistics. If you do a theory of stress in French, you have to write down a set of constraints, rank them for French, and say, this is my account of stress in French. When you've done that, you have just given, you just made a commitment to the typology of all possible stress systems. And there's no way out of it. There's no way not to do universal typology when you use this theory. The theory commits you to the claim that all possible re-rankings of the constraints that you've posited must generate possible languages, and all the possible languages. Okay, so the first innovation of optimality theory with respect to what we discussed earlier in harmonic grammar is constraint ranking as opposed to constraint weighting. The second innovation, which Benjamin was leading us to a moment ago, and also is the notion of faithfulness. So let me tell you a little bit about that, because this is another aspect of how the structure of grammar is characterized by this constraint-based perspective. Grammar ends up looking like a kind of dialectic between two titans, markedness constraints on the one hand and faithfulness constraints on the other. So if we have a constraint in universal grammar that says syllables should not have codas, then what are we doing with a coda in the word cat? Okay? Answer, there are constraints called faithfulness constraints that require that the pronunciation of a word equal its lexical form. So this is what we've stored in the mental dictionary. And faithfulness constraints insist that when we form words from morphemes from our mental lexicon, that the pronunciations must match what's stored in the lexicon. And those constraints, therefore, are going to push us to have structures which often are marked structures. So in this case, being faithful to this involves violating this. You can't satisfy both of those at the same time. Oversimplified. Okay, so what this is supposed to account for is why there is diversity in languages. There's diversity in languages on this picture because there are many different ways for this dialectic to be resolved. And each one is a possible language. There is no one way for faithfulness and markedness to resolve their conflicts. There are many ways, and they are many languages. Yes?
It seems to me that the architecture as a whole, the harmonic grammar architecture, is mute about the universality of grammar.
That's right. That's why.
In many kind of ways, even any kind of symbolic constraint, if I understand correctly. I mean, the system might may encode different kind of symbolism.
So
at the equal level of connection.
So what? So when we went from harmonic grammar to optimality theory, and the principles of optimality theory were developed, one of them being the universality, then of course we created a question which we still do not know the answer to, which is that at the micro level, what on earth is responsible for ensuring that your brain and my brain have the same patterns of weights, such as in both of our brains for no coda to be there, and to have the strength of that encoding be appropriate to our particular languages. Okay. I may say one or two words about that before we're done, but it's a problem that we are. The best I can say, I think, is that we can state what the question is with precision. Okay? I don't think it was ever any clearer how it is that grammar's universality resides in our brains. But at least now we know what that question really comes down to. If we think that grammar is this, and we think that it's realized in brains in the way that I suggest, we know what the question is, even if we don't know what the answer is. Before, all we knew was that somehow all our brains are the same. The evidence that optimality theory is a good theory of grammar?
The harmonic grammar.
Harmonic grammar?
I'm correctly proposing a model how to map symbols, the symbolic relation to the electronic network, those which we in fact do not know, and we do not know that the symbolic representation we have corresponds to our brain. We do not know that the connection is corresponds to what we have in our brain. So,
So,
I suppose you have some kind of evidence to support it, or at least behind it, the hypothesis.
well, what I'm still looking for is a way to test the hypotheses that symbol structures and the constraints among them are encoded neurally in the way that's described by this theory. I do not have any idea how to test that hypothesis. What it is we can look at the level of neural organization that can validate or falsify that hypothesis. But the perspective that, you know, it was pursuing that hypothesis that led to the theories of grammar that I'm telling you about. And we know how to test theories of grammar in ways that we don't know how to test theories of neural encoding. And so the empirical basis for the picture resides primarily at the level of, at the level of the grammars as opposed to the level of the neurons. I will say that in the book there are a couple of discussions of proposals that neuroscientists have made about how information is encoded in the brain, which can be seen as instances of exactly the same proposal that I'm talking about here, but not for linguistic representations, for representations of positions of objects in space in the visual field, for representations of the binding of properties to objects. So neuroscientists have made some hypotheses of their own based on their kind of evidence as to what neural encodings look like. And even though they don't speak directly to the encoding of linguistic representations, they use the same formalism. They haven't been talked about that way, but you can show that they are the same as this proposal here for the relationship between higher level and micro level representations. Benjamin?
It's really theoretical question because I may have missed something. So you said that there is this discrepancy between harmonic grammars and optimistic grammars that one can be better or not.
Yes.
But if they're one that if they're the type of harmonic grammar, then
that avoids that problem.
That realizes optimal theoretic grammar.
Well, all I said about that was that what you have to do is impose a restriction on what the weights can be. You have to say that they have to have this kind of exponential growth, and they can't just be anything. So that is, from the connectionist perspective, a very mysterious supposition.
Speaking of grammar, you could say that the stress must be on the higher symbol, unless there are millions of symbols to write. So strictly speaking, it would not be forced unless we constrain, but practically speaking, it would be.
That's right. That's what I mean by approximate. So in other work, which is discussed in the book, there's a discussion of some reason to think that there are actually reasons internal to neural network computation for why constraints that grow exponentially in their strengths might be singled out as having some computationally important property, namely that the kinds of optimization that networks do can reliably find the best state and not get trapped and fall into false states that look locally good but are not globally good. But we don't know about that with any kind of formal results. Okay. Let's see here. So optimality theory has been applied outside of phonology in syntax, semantics, and pragmatics. There's quite a bit of work on learnability. And I refer you to the Rutgers Optimality Archive for papers on these different applications of optimality theory. And increasingly, there are papers in there about harmonic grammar as well. Okay. So, oh, I see. I know what I have to do. I have to do this, don't I? That's what I have to do. Okay. All right. So, getting back to our questions, optimality theory provides answers to these questions that are different from answers that we've had before in generative linguistics. Grammars are structured as optimizing systems where what we use as our evaluation is a set of constraints which are universal but ranked in a language particular way. So it tells us precisely what's universal, the set of constraints, and the set of candidates, and the set of underlying forms. But crucially, the set of constraints. And it tells us how languages may differ, and in some very vague sense, why. Namely, the conflicts among all these constraints are adjudicated differently in different languages by different constraint rankings. So are grammars learnable in principle? Well, I mentioned a moment ago that there's been quite a bit of work on learnability theory and optimality theory. Here's a book you can look at if you want. The first results on learnability in optimality theory came out the same year as the optimality theory book did in 1993. It's been a part of the theory since the birth of the theory, almost literally. There's experimental work that tries to evaluate the nativist interpretation of optimality theory, which says that the universality of constraints is somehow a consequence of genetic encoding, that we are born with the knowledge of these constraints. That's the nativist version of optimality theory. It's not the only way that we could account for the universality of constraints. If it's possible by babbling and playing with your articulators to discover that certain kinds of articulatory patterns are dispreferred, everybody has the same articulators for approximation, and therefore it could be that there are learning mechanisms which are not dependent on genetic knowledge that could account for universality. But the nativist interpretation is that these constraints are encoded genetically. And what we've looked at is not the genes. I don't know how to do that either. But we have looked at whether infants and adults show evidence of knowledge of constraints for which they have been given little or maybe no empirical evidence. So that's what you would expect to find if the nativist version of the theory is right. So an early, well, this is pretty much, Peter died just before this came out, Jusic. So this, unfortunately, was a short-lived research program. But what we did was we looked at 6-month-old infants' knowledge of constraints favoring nasal stop sequences that have the same place of articulation, favoring MP over NP. And what we argue in this paper is that the expectations of a nativist version of optimality theory are borne out by the behavior of these infants. And there's a chapter in the Harmonic Mind which talks about that work too, in a more abbreviated fashion, as well as some more recent experiments, a few follow-on experiments. Iris Berendt and colleagues have been conducting, I'm one of the colleagues, I should say, have been conducting experiments on adults, trying to show that even though the language does not present you with explicit evidence about certain markedness principles or universal constraints, that speakers know them anyway. So, for example, in the Proceedings of the National Academy of Sciences paper, what we argued was that the behavior of Korean speakers when they're perceiving words that have consonant clusters are just what you would expect if they knew about the universal sequencing principles of sonority and onset clusters, even though the language has no onset clusters, arguably. And other studies with with English speakers, Russian speakers, Hebrew speakers have looked at various aspects of this question as well. So there's some evidence out there that purports to show that the expectations from an OT nativist theory might actually be right. Of course, they can't eliminate learning possibilities across the board. And what we did in the weirdest chapter in the book was we built a language acquisition device for optimality theory. So what we did was, according to optimality theory, these are the universal bits of knowledge of language, of grammar. And according to the nativist hypothesis, these things should be innately known. So what we did was we built a neural network and a set of things that we called abstract genes for encoding the knowledge required to grow these networks developmentally. That encoded all this information in the domain of syllabification of simple strings of consonants and vowels. CV syllabification, an aspect of optimality theory phonology that's been very well worked out. So what we showed was how to design a network that would have this knowledge, would not have encoded in it what the ranking of the constraints is, but would have learning procedures, neural network learning procedures, which would allow it to learn what the constraint weights are for the particular data that it's exposed to. One way in which this is, one shortcoming of this, one way in which it fails to fully do what I just described is that there's nothing in this network that forces the weights of the constraints to have this exponential property. So the fact that that's somewhat of a mystery at the micro level is manifests here in it not being a feature of the neural network model or the genetic encoding. So that's very much well, I should say we have a few speculative ideas about how to cope with this exponential weighting requirement that optimality theory imposes, but it's all very speculative at this point. Okay, so here, skip over this picture. It takes 80 genes, in case you're wondering. I was disappointed because, we only have like 20, 30,000 of them. That seems like a lot to spend on just CV syllabification. So I consider this to be an argument against the nativist theory. We just don't have enough genes to waste like this. Okay. I'm only going to say a very little bit about these last two things. Very just sort of orienting you to some things that are out there. How can quantitative variation and errors be explained? Well, notions from optimality theory grammar and harmonic grammar have been applied to these kinds of questions also. So this kind of question can be addressed at the macro level and at the micro level. Work has been done at both levels. So at the macro level, a lot of work has been done on stochastic or probabilistic versions of optimality theory as accounts of variation. For a given input, you don't always get the same output. Speakers are modeled as having a mixture of grammars, a probabilistic mixture whose structure is determined by the particular version of stochastic OT that the author is proposing. Arto Anttila was one of the first to propose that in speakers' heads, what we have are something more like a partial ranking of constraints, which means a mixture of rankings, all of which are consistent with that partial ranking, but which instantiate different relations that are not specified in the partial ranking. Sorry, that was completely incomprehensible. Forget that. Paul Boersma proposed a notion of stochastic OT in which constraints have numerical values, but not in the way that harmonic grammar proposes. Rather, the numbers reflect their ranking on a scale. And so if you have a number that's higher than another constraints number, then you outrank it with certain probability. The most sophisticated work in stochastic OT, especially in terms of learning constraints as well as learning their strengths is just published in Linguistic Inquiry, Bruce Hayes and Colin Wilson. There's work on this in The Harmonic Mind. Surprise, surprise. All right. That's a way of trying to use optimality theory at this symbolic level to characterize variability in grammatical behavior. At the micro level, I need to point out something about maximization of harmony in networks. And that is that when I said that the mathematical result was that spreading activation computes representations that maximize harmony, what I didn't say was that there are two senses of being a maximum. One is called a local maximum and one is called a global maximum. So a pattern of activation is a local harmony maximum if it has higher harmony than any pattern near it, or any small modification in the pattern will reduce its harmony. That's a local maximum. And most networks, especially deterministic ones that have no randomness in them, they do harmony maximization, but they're only guaranteed to find a local maximum. What we really want for grammar, according to the theories I've told you, is the global harmony maximum. That is the representation that's better than all the others, even ones that are quite different from it. That's the global maximum. And there are random network dynamics where activation spreads in a more random way, which in the limit of unlimited processing time can find global optima. They will find the global harmony maximum. And if you use these networks to do your harmony maximization, if that's your model of the micro level, then because they're stochastic, they inherently have variability in them. And if you rush them so that they don't take their time in finding a maximum, you make them make a decision relatively quickly, then they will make various kinds of mistakes, and you can study those as a model of variation and errors. And we've been doing that recently in modeling work that I've been doing with my colleagues at Johns Hopkins, Don Mathis and Colin Wilson, as well as Matt Goldrick. That's not in the book. Let's see. Okay. So the last 2 points I'll mention have to do with the last question, which is just how can the chronometric properties of language be addressed using grammatical theory. The fact that some behaviors take different amounts of time than others, and that's a major question addressed in experimental psycholinguistics. Grammar should speak to it. The kind of modeling I just told you about, in which we have neural networks that are doing a random search for harmony maximum, is one way at the micro level of looking at how long it takes for these networks to make their decisions. And what we've seen in the early work we've done is that, as you might expect, when the network needs to compute a relatively well-formed structure, it does it faster than when the output it's seeking is, while the best, not so great. So more marked structures take longer to compute, even when they're optimal, than less marked ones. At the macro level, there's a chapter in The Harmonic Mind that I did with Suzanne Stevenson, which tries to not address numerical questions about language behavior, but rather the kind of thing that sentence processing researchers study under the heading of garden path phenomena. So what we do is we look at the incremental assignment of optimal sentence structure to an incoming sentence word by word. So we assign the optimal parse to each prefix of the sentence. The first word, the first two words, the first three words. Each one as it comes in produces a prefix. We look at the optimal parse tree for that, and we make the hypothesis that processing difficulty arises when successive parses are inconsistent. So when the next word comes in and the optimal parse now involves reorganizing what had been optimal for the previous word, that's where processing difficulty arises. That's where people slow down dramatically. And what we showed was that you can account for a significant range of basic data on garden path sentences and attachment preferences where people prefer to attach incoming material when there are multiple options, at least temporarily. The crucial thing is that we were able to do this using constraints from OT syntax competence theory without proposing heuristics for parsing, without proposing sentence processing constraints, just using the constraints that already are needed for the analysis of complete sentences in competence theory. Those constraints, when applied incrementally, shed very interesting light on the temporal behavior you observe in online sentence processing reading. So you can read about that in the book if you're interested. So here's my conclusion slide. It's time for generative grammar to assume its rightful place at the center of cognitive science of language. Optimality theory and other frameworks can contribute now to research that address all of the classic questions of generative grammar that Chomsky has been putting forth as defining the field for many years. Okay? We don't have to just address this first question. What we know about the system of knowledge is already enough to allow us to say interesting things about the acquisition processing and the neural implementation, even maybe genetic encoding, although that's out there.
How can you say we know anything at all? And this is solely not hypothesis. No, we don't know. We have a model. It's an important difference.
What am I supposed to do to this, do you think? Let's see, what are my options? We don't have neural evidence that the proposal that I've given for how to take grammar and put it in neurons is correct at the neural level. That's what we don't have. But we have evidence on everything else that I talked about. Everything is disputed, okay? That's true. Look, when a scientist says we know something, that means we have a theory, we have evidence in its favor. There may be evidence that contradicts it. There may be other theories that have evidence. That's what it means.
Well, but I think what is required. Your theory is the status of string theory in physics. I mean, it's a neat mathematical theory. It's very elegant, but in fact, we don't have any evidence about it yet. So you cannot say, let's say, string theory may be the centerpiece of physics.
It's not true that we have no evidence about this. It's not true that we have no evidence about this. There's evidence on everything I said, empirical evidence on everything I said, except the neural encoding of linguistic structures and grammar. You can dispute it, and I would say that that is absolutely the right thing to do. All of it should be questioned and examined critically. Okay? That's what we're here for. And if you want me to be as modest as string theorists, if I work hard, I could probably do that. Well, let me say something stronger, okay? I think it is just very unfortunate to take the following position. We're just starting to do linguistics. You know, generative linguistics is just a baby. We don't really know anything, you know. We need 200 or 300 years to figure out the answer to question 1. Then we'll go on to question 2, and 3, and 4. Does that sound like a familiar position to you? Because it should, okay? That's the position I'm arguing against. I'm saying that what we do have is knowledge, not certainty. We have knowledge, right? Information theory. You can have information without having certainty, right? We have information. We know a lot about the structure of the system of knowledge. And we should put that knowledge to use in addressing all these questions and not just the first one, and not sit and wait until no one is disputing anymore exactly what the universal principles of syntax are. Thanks.